Oh, right, let's get right into it. Today, we're basically launching a deep dive investigation. We're going after one of the most frustrating problems in user experience: touch latency. Think of this as a hunt for lost milliseconds. You know that feeling, right? It's almost universal. That little bit of lag, it just makes an app feel clumsy, heavy, like it's disconnected from your own fingers. And that feeling, it's more than just a simple annoyance. It feels like a betrayal of what we expect from our devices. We expect them to be immediate. So let's frame this thing properly. The crime here? It's latency. The scene of the crime? Application development for Android, specifically with Delphi and its FireMonkey framework. And our mission? Well, is to follow the trail of those lost milliseconds, figure out exactly why this latency happens, and then build a rock-solid case with an arsenal of solutions. Now, to really understand the scale of this crime, you gotta look at the numbers. For something like professional audio, any latency over 20 milliseconds is pretty much unacceptable. And a single frame on a standard 60 Hz screen, that only lasts 16.6 milliseconds. The margin for error is razor thin. So when a baseline, unoptimized app starts at nearly 100 milliseconds of lag, you are absolutely gonna feel that. Okay, so where do we even begin this investigation? We have to start at the beginning, by dissecting the architecture of Android itself. We need to understand where these delays get introduced. Let's follow the complete journey of a single touch, from beginning to end. This entire journey has a name. In the industry, they call it the click-to-photon pipeline. It's the total time an input event, your touch, spends traveling through all the different system layers. So if we're going to solve this latency crime, this is the entire path we need to analyze and optimize. You see, to make things feel fluid, Android cleverly divides up the work. All the user interface events, like a touch or a scroll gesture, they're all managed on a main thread, the famous main looper. But the rendering, the actual work of drawing stuff to the screen, that's done on a completely separate render thread to really harness the power of the GPU. Let's use an analogy to make this crystal clear. Think of the main looper as a restaurant manager who takes all the customer orders. The render thread? That's the kitchen crew, the ones who actually prepare the food. So the manager takes the order, your touch, and passes it to the kitchen, the GPU, to draw it. This separation makes a ton of sense, right? You don't want to overwhelm the kitchen, but it creates this built-in, unavoidable delay between when the order is placed and when the dish is finally served. And this is where things get really complicated for us Delphi developers, because that touch event, that order for the restaurant, it has to make a very, very long journey. And on that journey, we find our prime suspect. Our suspect is called the JNI, which stands for Java Native Interface. You see, Delphi apps on Android, they kind of run inside this compatibility bubble. A touch event gets captured by the Java-based Android OS, it's given to the app's Java-based manager, and only then does it have to cross this critical bridge to get into the native Delphi world where our code lives. This image here really helps visualize the problem. Think of the JNI bridge as a slow, one-lane toll booth right in the middle of a high-speed freeway. Just crossing it can add between 16 and 32 milliseconds of delay. That's insane. That's the equivalent of losing 1 or even 2 entire frames before your code even gets a chance to see the event. And the evidence of this crime is something developers call stale input, or input rancio. It's that awful feeling when you're drawing a line on the screen and the line appears visibly behind the tip of your finger, almost like it's too lazy to keep up. What you're actually seeing is 1 or 2 frames behind the real position of your finger. Okay, so the diagnosis is pretty clear. We've got a long journey for every touch event and a really slow bridge right in the middle of it. So now, let's switch gears. We've identified the problem. Let's talk about our arsenal of solutions. We can actually structure this in 4 escalating levels. The first, and honestly, the most fundamental solution is all about good code hygiene. A super common mistake is to execute heavy, time-consuming tasks directly in the event handler. In our restaurant analogy, this is like the manager stopping everything to go cook a complex 5-course meal all by himself. It just blocks up the whole system. So the key here is to use asynchronous execution. And Delphi gives us a really powerful tool for this called T-thread force queue. It's basically like telling the manager, hey, just jot down the order right now. That's super fast. And then have the kitchen cook it in a second when they're free. This makes sure that UI thread, our manager, stays responsive and doesn't get bogged down. All right, so now that we've unblocked our manager, let's take a look at the kitchen, right? It's no use taking orders quickly if the cooking process itself is slow. And this brings us to our second solution, upgrading the rendering engine. And here, we introduce a technology that has been an absolute revolution, Skia. This is the 2D graphics engine that Google Chrome uses, Flutter uses, and Android itself uses. By simply enabling Skia in your Delphi project, you stop using the main CPU for all that drawing, and you offload all that heavy work to the much more powerful GPU. The performance benchmarks are just brutal. We're talking a 30 to 50% increase in frame rate. So we've freed up the main thread, and we've put a Formula One engine in charge of drawing. For most apps, this is fantastic. You're pretty much done. But for things like games or high-precision design tools, where every single millisecond is gold, we need to go even further. We need to start manipulating the hardware itself. Most devices you see out there run at 60 Hz. That means the screen redraws itself every 16.6 milliseconds. That's a hard limit, a latency floor you just can't get below. But modern devices support 90 or even 120 Hz. At 120 Hz, that cycle drops to just 8.3 milliseconds. You are literally cutting one of the biggest sources of system latency in half. Now, the downside is it uses more battery, so a smart way to do it is to request 120 Hz only during those intense interactions, like when a finger's on the screen. And this brings us to level 4, the most advanced technique of them all. And the philosophy here is simple. We're going to cheat. In a good way, of course. We are going to pull off a heist to bypass our main bottleneck, that JNI bridge, completely. So instead of patiently waiting for the Java system to deliver the touch event across that slow JNI bridge, we use something called the Native Development Kit, or NDK, to go straight to the source. We're basically sneaking in through the kitchen's back door and grabbing the event directly from the native Android system. This move completely eliminates that JNI toll booth from the critical input path. It's gone. Now, this all sounds fascinating in theory, but theory only gets us so far. We've got details from a very specific experiment with real hard numbers. So let's move to the climax of our investigation and look at the proof. Okay, check this out. This case study was done on a powerful Samsung Tab S7. The baseline app with 0 optimizations had a latency of 98 milliseconds. That's almost a tenth of a second. Just by enabling Skia, it dropped to 72. Then, unlocking the 120 Hz refresh rate brought it all the way down to 44. And finally, combining all the techniques, including that NDK bypass, they achieved a minimum of 32 milliseconds. From 98 milliseconds all the way down to 32. That's a total reduction of 67%. That is the difference between an app that feels sluggish and clunky and one that feels, for all practical purposes, absolutely instantaneous. But wait, there's another crucial piece of evidence here. It's not just about being fast, it's about being consistently fast. You know, think of it like driving a car. You'd probably prefer a constant, steady 60 miles per hour over an average of 70 that's full of sudden stops and jerky starts. Our brain is incredibly good at detecting these little inconsistencies, or what we call jitter. The initial test had a variability of 15 milliseconds. The final, optimized version had a jitter of only 2. The response isn't just fast, it's predictable, it's smooth. So after this entire investigation, what's the final verdict? Well, we can take all of these findings and synthesize them into a clear, actionable roadmap for any developer who's facing this exact problem. So here it is, the final verdict, a 4-level roadmap to fluidity. Level 1 is hygiene. Never, ever block the UI thread. Use T-thread force queue. Level 2 is acceleration. Enable Skia. It's the biggest win you'll get for the least amount of effort. Level 3 is hardware. Request those higher 90 or 120 Hz refresh rates on modern devices. And finally, for the elite, level 4, the NDK bypass for the absolute minimum latency possible. You know, we've seen that getting to true fluidity isn't about some single magic setting. It's about having a deep understanding of the entire technology stack, from top to bottom. But where do we go from here? What's the next frontier in all this? We've spent this whole time talking about reacting faster to a touch that's already happened. But what if an app could anticipate where your finger is going to be and start rendering at that future position before the touch even happens? I mean, we wouldn't be talking about just reducing latency anymore. We'd be talking about achieving negative latency through prediction. It's a really fascinating field, and it's a great reminder that this hunt for milliseconds, it never truly ends.